Okay. So yeah. So have you went through the content of the second week, or have you went through the first week content? How many of you went through the both weeks content?
Both.
Okay. So yeah. Hmm. So have you submitted the first week assignments, or how is it going?
Fine, sir.
Okay. Okay. So today we are okay. So somebody saying week two. Hmm. Okay. I guess 18th is the deadline, right, for the first week?
Yes, sir. For both, 18 is the deadline.
Okay, for both 18th is the deadline. So okay, so we have one more session, I guess, on the 18th, right? Right. So today we'll just go through the second week of content. I'll just brief you this first week also, just the PCA. What does that mean? And then we'll start with the second week. I'll just go through the content in a brief, and then if you have any doubts, we can just take that. And then in the next session, most probably we'll discuss some problems, maybe the activity graded or practice assignments. Okay, not the graded one, but if you have doubt, we can just give you the idea. Will not solve that problem, but I'll just try to make you understand that. Okay. So okay, so I'll just start with the PCA. Can somebody tell me what does that PCA does, and what are the advantages of PCA? What are the disadvantages? What are the issues and all? Can somebody just tell me a brief idea? What does that PCA mean? You would have went through the first week content, right? Okay, that is fine. Dimensionality reduction, but what does that do? How does that help you? Okay, change of basis, fine.
So it compresses the data, but includes the relevant information which should be there within the data.
Correct, correct. So you can see my screen, right? My screen is visible, right? Okay, I just wrote something for the week. So the week one was basically you would have went through the basics of PC and then the representation learning and then the projection of data points and all. Okay, I'll just go through the PC again, just the brief idea I'll give you. If somebody is not having the idea, you can just correlate with this. I'll just give you a basic understanding of that. If somebody has attended MLF, somebody has attended, maybe he would be aware of this same example that I mostly gave in machine learning foundation also. So PCA, if somebody is
Sir,
very,
just a minute.
yeah,
Sir, in PCA, the linear combination part, please explain that one. How the strong eigenvectors are related projected on linear combination.
okay, yeah, we'll go through that. So first
Yes.
I'll just discuss the PCA part. Okay, I'll just go
Yes.
through that also. Okay, okay. So PCA mostly is a dimensional reduction technique that everybody would be knowing that. So mostly if we have a dimensional, like if we have a data set that consists of like a very large dimension, okay, and that it can that we need to and that we want to visualize that. Okay, like for example, if I have a dimension, if I have if I have a data set and that consists of a dimension, that dimension is like more than 1,000 or 10,000 or maybe 1 million. Okay, and that you want to visualize that PCA, that you want to visualize those with the help of PCA, and you want to just reduce the dimensionality from some 1 million to some 10, so that you can visualize those maybe 2 to 3 3 or 4, just for the visualization purposes. Okay, so there PCA can help you. Okay, so there are like linear PCA, and the kernel PCA is also there. Many a times this PCA will not help you, but this can help you. Okay, So the basic one, I'll just tell you the basic PCA, the linear one, and then we'll go through the kernel also. So let's, for example, let's you have an example. I just gave you one data set, and that data set consists of two features. Okay. So F1, and there is a feature F2. And let's, for example, this F1 is something like F2 is like the height of a person. Okay, and then this F1 is something like the color of the hair. Okay, and the color of the hair, we have somehow got the data of some people from India itself. Okay, so we have X data set. Okay, and that X data set we have for some, and there is like 10,000, and we have a dimension, how many? Two dimension we have, right? And that will need to reduce it to the one dimension. Okay, so here the basic PCA generally what does that will try to reduce those features where where the variance is what? Variance is how? What? Can somebody tell me? In which direction we generally project the data? Where the variance is what?
Maximum.
Maximum.
Right? Maximum or
Where the
minimum?
variance is maximum.
Maximum.
Maximum, right? Or we can project the data where, so we are needing the direction, right? So we need a direction where the variance is maximum or the error is reconstruction error. You would have read reconstruction error is what? Minimum or maximum?
Minimum.
Minimum, right? So minimum is correct. So this is what generally we do. So let's, for example, I have some 10,000 of data and we have two dimension, and that I need to reduce. Okay, and that similar, the same things we'll be doing for the bigger data set also. So here we just are reducing from two dimensional to some one dimensional, right? This is what I'm doing here, and this is our data set. So you'll be agreeing with me, the color of the hair won't vary much, right? Let's, for example, I've just changed the color into some number, some, and then we are fixing the white as 0 and the black as 1, right? So but most of the people in India would be having black or gray hair, right? So mostly the value would be what? 0.95 to 100, right? Mostly it will be between 0.95 to 1, but the height of the person will vary, right? So the data set would be like this, right? Correct? Because F1 is the features, the color of the hair, and F2 is the height of the person, right? Till now it is clear, right? Is it clear?
Sir, I got disconnected. Sorry, sir.
Yes, sir.
Can you just explain, sir?
What
Correct. Just got disconnected for about a minute or so. Can you just explain, sir, from start?
Okay, I'll just explain you once. I was just going through the brief idea of the PCA, that most of like the first week is just the first week. I was just telling that I want to just change from two dimensional to one dimensional. My data set from one dimensional to two dimensional to one dimensional. Okay, using the basic linear PCA that you'd have read from the starting, the basic PC. Okay, so, and our data set is, I have collected a data set of some 10,000 people in India itself, from some village or from some city. Okay, and the data set consists of two features. The first feature is the color of the hair, and the second is the height of the person. Okay, and I need to build a model where I need to predict what? I need to predict the weight of a person. Okay. So I need to predict the weight of a person. So here, F1 is the color of the hair. So the values is like this. Mostly I told you already. Ki, the hair of the color is mostly gray or black, and I'm giving white as 0 and black as 1. So the values would be mostly 0.95 to 1. Okay, somehow we have changed this, so this is not our concern. Okay, so the value that we have got is from 0.95. So this is the 0.95 and 0, this is 1. Okay, but the height can vary because we are taking the randomly we are taking the height from our country, so that this can vary, right? Okay, so can somebody tell me which feature is important here to predict the weight of a person?
The height,
Height, right? Why height?
because it's having more variations compared to
Correct.
color of.
So because I have a variation like this from hair to hair, but if you will see in the color of the hair, so the variation is very less. That means what? Whenever we are building a model, so some weight is taking from the color of the hair and some weight he's taking, like that model is taking from the height, right? But in predicting that, the color of the hair most of the time the value is almost same, so I can reduce these features directly, right? So I can reduce these features and I can have the data set only F2, and with the help of F2 I can build a model, right? This was the simplest example that I can give you for the PC. Okay, this is how the basic principle, this is a basic principle. How does it work? This directly doesn't remove the features, but it generally takes out those direction where the variance is maximum. Okay, so in this direction you can see that which F2 direction the variance is maximum. That's why it has just removed the F1. Okay, is it clear to everyone? Till now it is clear, right? PCA, like the basic, how does it work and all, right?
Yes, sir.
You can see that screen, my screen you can see, right?
Yes.
Okay, so why are you like everyone is so silent? I can't understand. Uh, are you going like there is some other
Sir,
session
it's okay, sir.
or
So you're going okay, sir. We are understanding. Nothing
okay?
bothering.
Just left from office.
What? What? Can you repeat that? Can you repeat that? What you told?
Just left from office.
Okay. I can understand that. Okay, that is fine. So this was the basic example of the PSA, and the other example that I can give you is, let's for example, let's have the second example. So the second example can be, so this was the basic example, the first one where directly the one feature is removed directly. Okay, but that is not the case with the PCA. Like the PCA works similarly, but exactly doesn't remove the one features. Okay, and you can understand one thing also from here, uh like it was totally like the basic principle about the piece is like generally remove the d, like it's not related at all, the color of the hair is not related at all, whatever we have to predict. Okay, so that, and most of them, like for example if I have a model something like that x1, and then w1 is the weight that I'm getting from the color of the hair, and then w2 is the weight that I'm getting from the height of the person. Okay, so each and every time this data point will mostly be same, right? So this is what we can directly remove that, and then we can directly remove the f1 from there. The second example that I'll tell you, like for example there the data points are pretty simple, but we can have a data set like this, right? We can have a data set like this, and this can be the f1 feature and this can be the f2 features. So okay, so how does the PCA works here? Can somebody tell me for this type of data set? So here also from 2 dimension I need to convert to the 1 dimension. Okay, so if nobody is saying anything, I'll just answer this. So I need to get a direction, right? I need to get a direction, right? I need to get a direction. And that direction should be what? In that direction.
So is it like one being a straight line, one dimension is a multiple of another dimension?
What?
Like since we are looking at for PCA, that is from 2 dimensions, we want to arrive at 1 dimension.
Yeah, we want
Which
to,
means,
yeah.
yeah.
So you are correct. So the one dimension can be the mixture of the two, right? This is what you are saying.
Like it is a scalar and multiple or some kind of proportion of the another dimension.
So mostly this is what happens now in one dimension, that the direction, like for example, this is the direction that I'll get where the variance would be maximum, because the variance, you can see this is the maximum variance. If you will project the data points, all the data points, the variance would be maximum in this direction, in direction where the variance is maximum or the reconstruction error is minimum, right? So if you will project it, the data, so you will get that. So the variance, if you are projecting all the data, you can see that the variance will be from here to here. The variability, or you can say the spreadness of the data, will be maximum in this direction. Okay, and we are just worrying about the direction. We don't. So that's why it can be a unit vector also. Okay, so here we can get some combination of f1 and f2, and that will be a one feature. Okay, so we are reducing from 2 dimension to 1 dimension, and that dimension can be a mixture of f1 and f2, linear combination of f1 and f2. Okay, and that will be our the other feature, like means that will be the only features. Okay, now when we are reducing from 2 dimension to 1 dimension. Okay, till now it is fine, right?
No, sir. Can you please explain this again?
Okay, so here, so see, the what I told you is from f2 to f, like we have two features, right? And in the earlier example, that was a pretty simple example. Okay, so here the data set uh, was like this, where one data was the color of hair and the other was the height of the person. Okay, and here how did we remove the one features? Just we saw that we need
Variance.
those direction where the variance is maximum, right? So the variance is maximum in f2 direction, correct?
Hmm.
Okay, so similarly, we have to use the same concept here. PCA generally works on that principle only. So if we have this type of data set, right? So I need a direction where the variance should be maximum or the reconstruction is minimum. Okay, correct?
Yes, sir.
Right. So if you will see that this is the variance one v1 direction, the other will be what? The other will be this one, right? V2. But in V2, if you will see, so I'm telling, like I need to from 2 to 1 dimension itself. That's why I'm needing 2. That V1 I am considering. If somebody wants to just change the basis from 2 to 2 itself, okay, so the other one will be this one, V2. But here you can see that the variance is very less, and even if you'll calculate the reconstruction error, so that will be maximum, right? So that's why I'm not needing this one, V2. I'm needing this V1, because here the variability is maximum. So the two case you would have read, 1, 2, while solving the optimization problem. What is that optimization problem? Where your variance that you have calculated should be maximum. Okay, and that you are calculating, right? Arg max of that you would have calculated, the variance you have calculated, and for that you need that W, right? And the constant is what? Your constant is such that this should be a unit vector, correct?
Yes.
So that's why. So that why this is a unit vector. It can be from minus infinity to infinity, but we are just putting some constant on W, right? Because see, if we are not putting the constant on W, if we are just calculating such W such that the variance is maximum, that means what? We can just put this W as infinite, right? And at that infinite also, that some vector that is infinite vector, okay, at that point also the variance would be maximum. But what we are doing, we are just putting some constant on the W, because I need the direction. I'm not worrying about the magnitude of that vector, right? So I just am putting the unit vector. I need a direction. That's why I'm solving this problem. And while solving, you will be able to know that what do generally do. You generally calculate the covariance matrix and then calculate the eigenvector and eigenvalues, and corresponding to the maximum eigenvalues, the eigenvector that you get. If you have to change, if you need to get from 2 dimension to 1 dimension, you are worrying about only the one the eigenvector corresponding to the maximum eigenvalue. Okay, and if you want to change, right, for example, if you want to go from some 5 dimensions to some 2 dimension, okay, so here what you will be doing, you will be considering like the covariance matrix that you will calculate, like you will center the data, there are some 4 5 steps So you'll calculate the covariance matrix and then the eigenvalues and eigenvector. So you'll be considering what? You'll be considering V1 and V2. And V1 and V2 would be what? V1 would be the eigenvector corresponding to the maximum eigenvalues, and then the V2 would be the second maximum. Okay, this is the two feature that you'll be considering if you're uh, like from 5 dimension to 2 dimension, if you want to use for some data set using the PC. Okay, is it clear till now?
Yes, sir.
Okay, so now let's start with the second week. So this was the basic principle and PCA that you would have read, or if somebody is having doubt, you can just scroll. Like if you have now also doubt, you can just go through the lecture. Like I would have explained 10 to 15 minutes, and that will clarify your doubt. Okay, but if you have any doubt from the week 1 also, you can ask me, but not now. We'll just go through the week 2. You can ask me later. You can just mail me, or whatever you want to do, you can do that. Okay.
Sir, I just wanted to ask that when we reconstruct the data, how it is a linear combination of the top k eigenvectors.
Okay, so linear combination. So okay, while doing the reconstruction.
Yes, sir. Yes.
Okay. See,
While doing the reconstruction, like the image data set which the sir has taught us. So how numerically it is happening? I just wanted to have a
okay.
look at it.
So in the first, okay. So I'll just tell you. Like for example, you have some image. Okay, and that image will be what? So in the lecture, sir has take sir took some images. Okay, so let's for example, I have an image. Like we'll be having a n equals to some large chunk of images.
Sir,
Like
in the PC algorithm,
huh,
when we reconstruct the data, so I just
yeah.
want take a small data set and just reconstruct the data and how it is linear combination. I just wanted to visualize it.
Okay, so I'm not getting your point, but I think so. You're asking this, like for example, if I have a data set, like I have some data set, okay, and that
Yes, sir.
data
You
set
can
is
just explain it also. Nothing to.
okay. Like for
Yeah.
example, I have some data set xn to xn, right, where
Yes.
xi belongs to some
Yes.
r100. Okay,
Yes.
so xi is mostly like for example, I have just converted from some 100 to 3 dimension, right? Okay, so my xi would be what? Xi transpose W1 W1 plus Xi transpose W2 W2 plus Xi transpose W3 W3, right? Correct. And this is the W1
Unmute.
W2 W3 is what? This is simply the
These are
eigenvector
the
that you've got.
eigenvectors. Yes.
Okay, right. So if you are just storing, if you just need to know, so if you are storing the data, okay, so your representation will be what? Representative will be what?
Projection.
This W1
W1,
W2
W2.
W3, and
Yes.
that will belongs to what? How many? R100, correct?
Yes.
That will be an R100. Okay,
Yes.
but you need the coefficient also. That coefficient will be what? The projection, right?
Yes.
So the coefficient you can write, like the coefficient would be what?
Projection.
Xi transpose Wi, Xi
Yes.
transpose W2, and Xi transpose W3, correct? And that will belongs to R3. This is what you are asking, right?
Okay.
Okay.
So this
So
would be XI or X1.
this should be Xi. This is Xi.
Yeah, XI.
Hmm. Okay. Yeah. So okay. So I'll just Yeah, this was fine. So in the first lecture, so I'll just give you that eigen phase, just Harris dot. Okay. So in that, is there any doubt in that? I guess there was not that much was there. He just told about the example of that eigenface and how does that the time complexity. Okay. So there it was not. So I'll start with the issues that we have in the PCA. Okay. I hope if you have any doubt in this first week that lecture that sir taught about that eigenface stuff. If you have any doubt that you can ask, but the mostly the stuff that starts from the second and the issues that is concerned, issued or the concerned, right?
Sir, I have a doubt in programming. I can in programming I can't see the data set, but how can I say how do I apply that thing so that it doesn't know that?
What you
I don't
can't see
know.
the data set where
Yes,
where
programming I open into the collapse. So then they are written some codes in the first cell. After the cell, they ask some question. The sample data set. I think how many row or column they are. So, but I don't know how to execute
where
that thing. Can I share my screen so that it will?
in week one or where
Yes,
collab you
week
are
one
saying?
week one programming assignments.
Okay. That I need to check. You can maybe message me after this session. Okay.
Okay, sir.
Hmm.
Okay.
So for programming assignment, the deadline is 18th only. No?
No,
Okay.
programming assignment don't have any uh date. I
There
think
won't be
it is for
deadline for that programming assignment,
it
I
is
guess.
only for practice.
But it was written over there.
Okay, it
Date
is
is
on
18th.
16 October. I think that is the extra
Yeah,
bonus
two
for the
dates are
bonus.
mentioned.
Okay, 2 days means I'm checking. Okay, I don't know.
Yes, you can check.
Okay. So I'll just start with the our second week that we're here for discussing the second week. So the first concern, can somebody tell me what is the first concern?
So it is the time complexity. So
Time complexity, right? Okay.
calculating the involving the calculation of the eigenvalues and eigenvectors
Yeah.
may take a lot of time.
Yeah. So time complexity, why? Because we need to calculate the eigenvalues and eigenvector, right? We need to calculate the eigen and value and eigen. Like for example, there was a question, not question. There was a like for example, I have a data set, and that data set consists of like n equals to some 10,000 datas, and I have the dimension equals to some 30K, right? So for in these cases, what is the covariance matrix? Okay, can somebody tell me the size of the covariance matrix?
Say 30K cross
D
30K.
cross D.
Okay, that is 30K cross 30K. Correct? Okay. What's the formula for that covariance matrix?
Uh,
X transpose 1 by n summation I
X.
want to add X transpose.
Xi into X.
Xi transpose.
X
Right? Xi is what? D cross n, and this is n cross D. Right? Okay. So you have that covariance matrix as this one, or you can write like this also, 1 upon n x transpose. So this is simply d cross n, and this is n cross d. So you'll be having the covariance matrix as d cross d. Okay. And now we have that dimension very large, right? So we have this covariance matrix in the form of what, d cross d, and that is similar to what, 30K to 30K. Okay. So in this case, what happens? Okay. So can somebody tell me okay, when we do the matrix multiplication, so here what we are doing while calculating the eigenvectors. Okay. So we are doing a very large matrix multiplication, right? So in this case, the time complexity generally go in what, dq. So it's not important to know how does it came, but mostly it came because we are using in the multiplication itself, we are using some 3 loop, right? If I'm fixing, so let's for example I need to multiply the some a and b. Okay, so there will be some values from I to some n, and then here also will be I to n, and then I'm fixing some c equals to something like Cij, and Cij I'm fixing it as 0, right? So I'll be using what? You'll be using 3 times the loop, right? One I'll be fixing I and then j, and then I'll be starting c with 0, and then I'll be increasing the size of that. So mostly it's like then the in that case the time complexity will be mostly that dq. Okay, and that's why if the dimension is very large, so what will happen, it will take it will take a lot of time to uh, calculate that eigenvalue and eigenvector. Okay, so that's the one issue. And that example was what, that face recognition that sir has told, because in whenever you will be having some image stuff generally gets break down into what pixel values. Okay, and if you have pixel values will be like, if you have something image right click where it has written 1 itself. Okay, so the pixel values will be get broken out, like it will be, the pixel will be what, like if I'm just for example it's a 64 cross 64 pixel. Okay, so it will be what, 64 rows and 64 column, and each will be having some value. So that image itself will get changed into 64 into 64. So 64 into 64, whatever you're getting, will become the dimension for that image. Are you getting my point? So this is a huge, right? So like for,
The
did you get the
dimension is
point?
64
Yeah.
and n is also 64.
No. 64 into 64. So whatever the values you are getting, that itself is a dimension. And I didn't told
Yes.
you anything about the number of images. N can be anything. Like for example, some 10K. See what happens. Let's for example, I have
Yes,
a
sir.
image,
In the
small
lecture, sir
image,
has
and
taught
that
d
is
cross d into n.
okay. So let's for I'll just tell you once more. So I have a image, and that I am telling you it's a 2 cross 2. Like I just calculate 2 cross 2 pixel itself. So I have written something. So the value here is 0.2. So and 0.2, it's all the values whatever I'm giving depending upon the color that is there. Okay, so for 0 I'm fixing 1, and for the black, for the white I'm fixing 0, and for the black I'm fixing 1. Okay, so the resolution of the color in that pixel will give you the value. Okay, like for example it is 0.5 or 0.6 and 0.7. Okay, so now this 2 cross 2 pixel, let's for example this will become a one feature f1, this will become second feature, this will be third feature, and this will be your fourth feature. Okay, so that image, whenever you are taking some image, okay, so that will be having a huge dimension, right? That I told you the reason. This I just gave you for the example, but if I have like 64 cross 64 or whatever I'm taking that pixel value, so that will become a huge dimension. Okay, so in those cases where the dimension becomes very huge, and we already know the time complexity of this algorithm is dq, so it will become difficult to it will be calculated, but it will take time. Okay, so that's why this is one of the concern. Okay, for us. So how are we going to fix that? Okay, how are we going to fix that? Can somebody tell me how, if you have went through the lecture, how the final conclusion, how are we going to fix that?
Instead of D, we are taking N.
Okay, so instead of, so somebody told instead of
D, dimension D, D is very
we are
large
taking
than
N.
N. We are
Okay, because
transforming that
and
D to N. And
yeah, because here the D was very large compared to that N. Okay, so how does that help if I'm taking N? How does that help?
Because in covariance matrix, we are finding the covariance matrix. So in
Yeah,
covariance
correct,
matrix, it is a D cross D. Instead of if you do the N cross, if you do the N cross N matrix, then it will be very time efficient. But one
Yeah.
thing is, sir, one thing my doubt. Here the N cross N is a small metric, and D cross D is a very large metric. And
Huh.
So whatever eigenvalue present in n cross n matrix, that also be present into the d cross d matrix.
Yeah. So
And
yeah. So
that
this is a
d
linear algebra that you read in MLab.
yes,
So whenever you have some x transpose x transpose or x transpose x, so this is our exact data, like the exact for
yes,
whom you should be calculating, right? This is a d cross d, right?
yes, sir.
This is what n cross n. So
N cross
nobody has any doubt in like how x is d cross n and x transpose is d cross n, like n cross d. Do you have any problem in, like, if you have any problem, you can just ask me. Otherwise, it will be difficult for you to go through MLT for sure. Okay. So I hope nobody is having any issue in the dimension at least. Okay. So let's x transpose x is like what, n cross n. Okay. So whatever the non, so see, so whatever the eigen values, non-zero eigen values you'll be getting. Okay. So you'll be getting similar for here also. But okay. This is what we were asking, right? For x transpose
But
x and x
but sir,
transpose.
in SBD we are doing similar kind of thing, but there we are getting the non eigen vector also.
Yeah,
Non
see,
eigen
if for
zero.
example, let's for example, you are x transpose, your x transpose x is some 2 cross 2.
Yes.
Okay, and here x transpose x is 1 cross 1. If you got 1 as a eigenvector here, so here the 1 will be, yeah, you should be here, 1 will be the eigenvector, okay, and the other will be 0.
But so similar concept is there in SBD also, but SBD we found that sometime it is a non eigenvalue also be, non zero eigenvalue also be there, eigenvector, sorry sir, non zero eigenvector also be
No,
there.
I'm just talking about the eigenvalues, not the eigenvector. Till now, I haven't told anything about the eigenvector.
Okay.
Okay,
Okay, if
so
it is
okay,
eigen, okay,
yeah,
okay,
yeah,
sir.
go ahead.
So I need to check. So I think that in SBD also we are getting non-zero eigenvalue. I think, I don't know. I need to recheck it.
Okay, so you can check that, but see, the eigenvalues will be same. That is for sure. Okay, so the
Okay.
non-zero eigenvalues for x transpose and x transpose will be same. Okay, and the eigenvector will change a bit, but the
Yes.
eigenvalues will be same. Okay.
Yes. Yes. We can spam it so it can be changed. We change it.
Huh. So should I go through all the proof, or should I directly say the conclusion for this case, or should I go through each and every step? Just tell me. Otherwise, we already passed 45 minutes. Should I go through each and every step?
Yes, sir, that would be better.
Yes, sir.
Start. Okay. So for our case, what was the dimension? The X data set. We have X data, right? This is the data set. This is X1, X2, right? Correct? This is D cross N. And we have that example where D is very, very large compared to N. And we need to fix that. So we are started fixing that problem where the value of D is very large, where the dimension is very large. Okay. So let's start that. And we have X. So C is simply here 1 upon N X transpose. There won't be any problem. This is similar to 1 upon N summation of xi transpose. There won't be any problem till now. So let's go ahead. Why we are doing all stuff? Because in calculating xx transpose we are getting some bigger dimension, and that's why the time complexity is very high for this. So that's why we want to get some, we want to calculate the eigen values, okay, by some different method, so that the complexity, the time complexity should reduce. Okay, this is what we are trying to do. Okay, so this is the only thing that we are trying to do, because from here eigen vector was very difficult to calculate because of the large dimensions. Okay, let's start. Then let's, for example, this wk be the eigenvalues, eigenvector, and that will be the eigenvector for what? The kth eigen value, correct?
Yes, sir.
So if you have like lambda 1 to lambda, so that is like understood, I guess, lambda 1 to lambda some d, and then you have some w1 to wd. So there would be some lambda k, okay, and corresponding to that we have a eigenvector, right? So what is the basic definition? What is the definition of the eigenvector? So if you are multiplying some matrix, like for this covariance matrix fish wk, so what should I be getting here?
Lambda W,
Lambda k.
lambda K.
Why? Because whenever you are multiplying that matrix with some this with this eigenvector, that will get converges to, like, it should not go in some other direction. It should be in the, it should get what you can say, the scalar multiplication of that eigenvalues. Okay.
So from the data set, how to get
What?
this? So from the data set, like what we have,
Huh?
x1, x2, and so on to x any vectors.
Hmm.
So how to get the top k the eigenvalues, sir?
Okay. Top k eigen. So see,
Just from the matrix.
from the covariance matrix only, right? Covariance matrix. Whenever you are solving that, whenever you will solve for the eigenvalues, you will get some eigenvalues, right? Let's, for example, you have a covariance matrix of x transpose, and that is 2 cross 2 itself. Okay. This is a eigen. So 2 0 0 3. This is your covariance matrix. Okay. If you have this covariance matrix, what is the eigenvalues? What is the lambda 1?
2.
Okay, so you have like, okay, so this is 3, and then lambda 2 is, I just arrange that in the ascending order. Okay, and then similarly you can get the eigenvector from here, okay, corresponding to that eigenvalues. Okay, so similarly we are doing it here. So we have that wk. So we are just wanting to some other method to calculate the wk. Okay, this is why we are here to get the, how will we calculate the wk without calculating the covariance of xx transpose, because this was very time consuming because of the time complexity. Okay, so this is a definition, right? And this c, how, what can you write for the c? Can be written like this, that I told you, right? Can you write like this?
Yes.
Yes.
Okay. So this wk, can you write like, it's a combination of some that data points. You can just write this n lambda k, and then xi transpose wk, and this xi. Okay, so wk is what? Wk, you can write this wk. So x is that and alpha k. Alpha k is what? Alpha k is this one. Okay, so in that, if you have to calculate wk, you should be knowing about the alpha k. And if you have to calculate alpha k, you already know that to calculate the alpha k, you should be knowing the wk. So this becomes a what? So which came first? Like chicken came first or egg came first? Okay, this is like that, right? So it becomes a chicken and egg problem.
So, but sir, I have a doubt here, basic, which is the covariance is d by d, right? Covariance matrix dimension.
What covariance is?
Matrix and computed dimension. It will be d by d, right?
Yeah, covariance is d by d. That is fine. Covariance
Yes,
is
sir. So, so eigenvalues also will have, it will be like d, right? Eigenvalues.
eigen. So for the covariance matrix, I told you, like, see, for the covariance matrix xx transpose, there will be some d eigenvalues, right?
Yes, sir.
Eigenvector and eigenvalues.
Eigenvalues are on the d.
Huh. So what's your doubt here?
So for d eigenvalues,
Huh?
my question is, first of all, how to get these d eigenvalues?
So
Yeah,
this is
the
what we are
usual-
solving, right? So we can get the eigenvalues directly, but the problem is this was a very lengthy method. So d, to calculate d, it's a very time consuming, right? Because d was very large,
Yeah.
and you don't have to calculate manually. The computer, that the library will do for you. Okay.
Yes, sir.
So here we are just understanding the concepts. So you don't have to manually do that. I just told you for the 2 cross 2 matrix, but nobody is going to ask you how to calculate. If somebody is asking you, they're just asking you from where that eigenvector is coming, from where the eigenvalues are coming. Okay, so this is from the covariance matrix itself. Okay, right, D cross D. Right?
Yes.
Okay, so WK is simply the linear combination of the data points, and you have the data points xi, right? And this is what, if we have to calculate alpha k, so alpha k consists of WK, right? So we have to first calculate WK. For that, we need alpha k. But alpha k, if we are seeing that alpha k needs WK, so that becomes a chicken and egg problem that you would have read in MLF also. So which came first, chicken or egg? Okay, so that is like typical to solve, because for whatever we are trying to get, again to calculate that, we need that self. Okay, so let's move to the other definition, and then maybe we'll come to this definition. We can just write it as a equation 1. Correct? So
Sir,
this
can you explain why this is WK is XT WK?
what WK is?
XT X transpose WK means how is it? How do you get this?
No, WK I wrote it like this. From here I wrote it like, I just wrote the lambda k here, so it becomes like this. Okay, and here I wrote the x, and x is simply what? X is the matrix xi, x2, like this till xn. And here alpha k is what? Alpha k is belongs to Rn, and alpha is k is alpha ik, alpha jk, like this, alpha n. So it's a vector in n dimension. Okay, this is how I just wrote it like this. So this thing I just wrote it for the simplification. Okay, x into alpha k, and alpha k belongs to some Rn, where alpha k is a vector like this. Okay, and x is, we already know this data set, right?
Right, sir.
Okay, so till now, so I just wrote this equation. Wk is equals to what? Wk is equals to what? X into alpha k. Okay, and you already know about the alpha k. Alpha k is what? Alpha k belongs to some Rn. Correct? Okay, so this is our equation 1. I'll come to this equation again, because we need to prove something. Okay, so then, so now, so from, we already know this WK is what? WK is x alpha k, and this is from the equation 1 itself. From the eigen equation, we already know the eigen equation. What is that eigen equation? C, if we'll multiply some matrix with the eigenvector, that will be a scalar multiplication of eigenvalues into eigenvector, right? Is this clear till now, or should I repeat anything?
Sir, only that equation. Could you scroll up?
Okay, this equation.
Yeah, WK. WK is there on both sides.
So WK was there. See, WK is there on the both side, right? This is the eigen equation, right? That we generally write. Any matrix,
Yeah.
that matrix times that eigenvector is equals to what? The scalar multiplication of the eigenvalues into the same eigenvector. Okay, I just wrote it like this. See, we can write it like this. C is a covariance matrix. We can write it like this, right? See, we already know it's a 1 upon n summation of xi transpose. Correct?
Yeah, sir. Only thing is that xi transpose into WK, where xi transpose into WK is okay. Whereas we take an xi into the other side, whether is this a matrix multiplication? Is it okay?
No, it's just a, see, it's you can do this. This is a summation of xi transpose. Okay, so you can do that.
Okay.
Okay, and then we'll be just coming up with WK, where we'll just write x, and this also you can write it like this. WK is what? WK is what? X into alpha k. X is what? I wrote it like this. and alpha we already know, alpha I, alpha nk. This is what, this is simply the summation. If you'll just multiply it, xi alpha ki, right, where I is from 1 to n. This is what, this is multiplication only. So this is what I wrote. Fine.
Yeah, sir. Only that doubt, but it's okay, sir. In further, it will get clarity.
So, sir, what is the vector alpha k? Sir? What is it? Alpha I n? Sir? What is it? 1 n? Sir? What is the vector actually?
This is, see, we have this alpha k, okay, multiplied with x is equals to wk, right? Here alpha k is what? Alpha k belongs to Rn because it's a vector in n dimension, where you can write like this: alpha k1 to alpha kn. Okay, and this we have to calculate. Why we have to calculate? To get the value of this eigenvalue. And why we are calculating this? Because we don't want to calculate from the covariance matrix, because it was d cross d. Is it clear to everyone till now? Shall we move further?
Yes, sir.
Okay, so I'll just so otherwise it will be yeah. So we move further, so we'll move now. So equation 1, we already know. Equation 1 is wk equals to x alpha k.
Sir, one
Huh.
question, like C is 1 by n xi x I xi transpose summation, so that becomes a value, right?
What,
And
what?
how it will be divided dimension?
What?
C, that is 1 by n xi transpose, right?
Huh.
So this is a scalar value.
Xi is what? Xi is what? If you are writing, you are asking for C. How is C n cross n? D cross D. This is what you are asking.
Yes, yes.
Okay, so C is what? 1 upon n x transpose. X is what? X is a data set, right? Data set is what? Xi, x2, like this, xn. Correct?
Yes.
So we have how many dimension? I to D dimension, right? So this is D cross n, right? So X transpose will be what? N cross D. So if we'll multiply this into n cross D, so we will be having D cross D.
Divided.
Correct?
Yes. So
Okay.
that summation, if the x transpose is there, then that becomes a dy d dimension. But if it becomes a summation, then it will be again dy d.
Where summation? Which summation?
Can you please go up, sir? हाँ यहाँ पे yes, here 1 by n summation of xi transpose.
Okay, so what are you asking here? This xn, this x is a data point.
No, just above that.
This one,
उसके ऊपर उसके ऊपर
उसके
ये
ऊपर.
वाला.
Okay.
हाँ,
Here
this
also
one.
it will be d by d. Yeah. It's just a
So
matrix, right?
that summation, like you mean to say that after multiplying that xi and xi transpose, whatever it will come, if I summation sum up them, still it I will get d by d.
Yeah.
Okay. Okay, sir.
Okay.
Sir, and about size of WK, sir.
Okay. Wk is what? This is a covariance. This is eigenvalue, right? Eigenvector, correct?
Yeah.
So okay, just think about that. What should be the
It is d by 1, sir.
it should be d by 1, right? So yeah. So this is fine, I guess.
Excuse me, sir.
Yeah.
Sir, please upload this recorded in the calendar, sir, because I have class at 7 p.m.
Okay, I'll upload this. Yeah. So sure, I'll upload it.
Okay, thank you, sir.
Okay. So now We
Sir,
have
only thing I have, there is a problem is that we are getting d by d when xi is multiplying with xi transpose, and that is multiplying with wk eigenvector as d by 1. So at last we are getting d by 1 is the our at last multiplication output.
correct.
And when we are doing x transpose into wk,
X transpose into WK. Where we are doing X transpose into WK?
we take an xi outside, na, sir, in that sigma, in that equation, above equation. Yeah, we taken in this particular wk, which it is there with xi transpose, it is being there, whereas xi, another xi, it is taken out in the other side.
Okay, so let's take again. So what was your doubt if we are writing?
Yeah, that is x in 1 by n sigma
Hmm.
x into xi transpose outer bracket wi.
This is WK.
Yeah, and we rewrite this particular equation with taking xi outside. In the left hand side, we have taken xi outside from the sigma.
Oh, no, we have not taken out xi from the sigma. It's already there. It's there, xi transpose WK xi. This is why then it's already there, right? The sigma is, we are not removing the sigma from anywhere.
No, we are not removing, sir, but matrix multiplication A into B into C is not equal to B into C into A, na, sir.
Okay, I guess there is some catch here. Okay, I'll just discuss this. I'll come again. Okay, I'll come again here. Okay, so I'll just
Yeah, yeah.
complete this and then I'll come again here. Okay, that will be fine. Or else, maybe we can discuss it later also. But I'll just discuss it in the maybe in the Sunday meeting also. Okay, so that point
Right,
I'll
sir.
discuss. That I'll just note it down. Okay, this step, right?
Yes, sir. Yeah.
I'll discuss this again. So I guess apart from that, everything is fine, right?
Yeah, sir. Everything is.
Okay, so that was otherwise, yeah. So this is x and this is alpha k, right? And this was our equation first, right? And if I'm multiplying, and the second equation that we can get is from the like this will satisfy the eigen equation also. So if we are writing wk equals to lambda k times wk, correct? Fine. And this we can write it like this: 1 upon n x transpose. I can write it like this, correct? WK. And then
But sir, there sigma is also present, right? 1 by n sigma x and x transpose for the c value.
where?
C for the c, what is the c? Like it will be 1 by n summation x
No, no,
transpose,
if we'll
right?
multiply, that will come at the same.
With
See, X is
multiplying.
what? X is a matrix itself, right?
Yeah.
Fine. X is a matrix itself.
Mm-hmm.
And this is what? X1. If you will multiply each everything, will come at as a 1 upon n summation of xi and xi transpose. Okay. We are just writing there in the form of matrix. Okay. And the same thing happened here also. Okay. I forgot that. Did you get the idea why it was happening? Because here we are writing in the form of summation. Okay,
Okay,
here we are
okay.
just writing in the form of matrix
Total.
form. There
Total.
we were not writing in the form of matrix form. Okay, so
Mhm.
that's why the summation will be same. Okay.
Okay.
I hope that is clear to you also, whoever was asking that step. Here this is not in the form of matrix, we are just writing in the form of summation. Okay. Here the xi is what? Xi is in the form of RD, correct?
Yeah, sir.
I hope this is fine now, right now. Okay, so here I guess so if we, so here the WK, and then we can write it like this. Okay, so we can replace this with x alpha k, right? And if we are replacing this with x alpha k, and then we have lambda k also, right? So if we are writing here 1 upon n x into x transpose wk equals to lambda k times x alpha k, correct? And then if you are pre-multiplying, this is what you're doing, and then if we are pre-multiplying that n can go there, so x
So this
trans
lambda k, how did you keep from where? Because I do have the. So could you please
what
tell me?
lambda will be there, right? Because lambda, so this is the eigen equation.
WK was the acha. See WK is lambda k WK. Okay.
Okay, so lambda k will be there, and then you have this wk. I just put the equation first here.
X alpha u.
Okay, so now we are left with what? X transpose x, and then again x transpose. We are left with how many? What is that? Did we do any mistake? Is it fine till now? Okay, so this x wk also we can replace with x alpha k, correct? So this x transpose x, and then x is there, x transpose, and wk we can replace with x alpha k from the equation 1. Equation 1 you already know, right? Lambda k can be shifted anywhere because it's a scalar quantity. So x transpose x, and then lambda k alpha k, correct? Is there any doubt till now? This x transpose a x, we can replace it with a. So a square alpha k equals to what?
So can you please repeat from where you pre-multiplied by x transpose? Because I think I got confused here in the second line. I got confused.
Where?
So just the first line where xt, I understand till where you pre-multiplied with xt, x transpose.
Huh?
And then you.
This is C, right? This is C, and this is WK. This is the eigenvector, and again this is the eigenvalue, and this is the eigenvector x into alpha k that we have taken from equation 1 itself.
Yes.
Okay, and now we have pre-multiplied x transpose. So if we are multiplying x transpose, that will become x transpose x. Okay, n we can shift it anywhere because it's a scalar quantity, right? And then again this x transpose x came here. Again x transpose into this w, we can write it like x into alpha k, correct?
Right.
Okay, so we are left with what? A square. A we have just taken x transpose x as a. That's for example, just for the simplicity. Now we are left with a square alpha k equals to what? A lambda k alpha k, correct? Why we are doing this? Because we need to calculate alpha k, because alpha k was having wk itself, that eigenvector itself, right? To calculate wk we were needing alpha k. To calculate alpha k again we were needing wk. That's why we are focusing to calculate alpha k with some other method, right? Okay, so now we are left with what? This equation, right? This equation you can say as a equation 2, right? So this is what? A alpha k equals to alpha k lambda k x. This is the equation 2. Till now it is clear, right, everyone?
Yes, sir.
Okay.
Sir, can you roll back where alpha k's explanation was given upwards?
Where?
where WK is equals to lambda K alpha K. Sorry, X alpha K.
Yeah.
Okay.
What do you want to like ask? Can you tell me?
I just want to understand what is alpha K here.
Okay, so alpha K is what? Alpha K is simply it's in Rn dimension. Okay, and alpha K is here.
Okay.
Alpha Ki to alpha Kn. Okay, and there X is what? X is simply the matrix of the dataset. Okay, and this is what we are calculating. Alpha K we are calculating to get what? Wk. Okay, so this is the one equation that we have got. And from the basic stuff, we can get one more equation. What is that one more equation? Like for example, again from equation 1, Wk is equals to what? X into alpha K, right? If you are multiplying this Wk transpose both side, if you are multiplying Wk transpose both side, what will happen? So Wk is what I told you in the starting. Wk can take minus infinite to infinite value, but the constant was what in the PCA? The constant in the PCA is to make W is as a unit vector, correct? Why? Because while we were solving that optimization problem to maximize the variance, we can take any unit. We can take switch off the AC. Yeah. So while taking the this eigenvector while calculating the PCA, we were solving the optimization problem where we need to maximize the variance, correct? While maximizing the variance, we can get any vectors, right? Vector can be minus infinite to infinite. So infinite vector we can take here, right? But that will not satisfy our conditions. For that, what we are doing, we are fixing the constant as such that the W it should be a unit vector. Why? Because we just need we should be taking care of the direction only. We don't want we are not caring about the magnitude, right? So that's why we are needing W as a unit vector. Okay, so here this side it becomes 1. So 1 equals to what? Alpha K transpose into X alpha K. Can somebody tell me what will happen here? 1 equals to what?
X alpha K whole
transpose X.
It's the alpha K transpose
alpha K. And
alpha K transpose
X
transpose, right? And then X and then alpha K, correct?
Yes.
This equals to 1 equals to alpha K transpose. This we have already taken as what? A. We assume this as A, right? We assume here you can see that. We have already X transpose X. We have assumed it as A, right? Okay. So and this is alpha K. So this is the equation 3rd. So now we have equation 2 was what? Equation 2 was again in the form of alpha K. This is what? A alpha K. So whatever alpha K we will get, that should satisfy this both condition, right? What was there?
So will A here be a scalar, sir?
Can you repeat that? I didn't get your question.
So will A here will be a scalar or what, sir?
A is a matrix, right? A is a matrix of n cross n. A is what? A is X transpose A, right? X transpose X.
Yes.
X is what? X is D cross n. Sorry, n cross D. X is a D cross n, but X transpose will be n cross D, and this is D cross n. So you'll be having n cross n matrix. This is a.
So X is actually n cross D, right?
X is D cross n. See, X is what? X is your data point, right?
Yes, sir.
And how you are writing your data point? The x1 like this.
Oh.
Okay, let's for example, x1 is equals to some vector 2 4 that has two features. The first feature value is 2 and the second feature value is 4. So you are writing like this 2 4.
Okay.
Similarly you can write it like
Matrix
3 6. Okay, so this equation, this 2 cross 2, this has two vector and two dimension also.
Oh,
Correct?
okay. So matrix, okay, matrix representation of the data set, right? Okay. So
Okay.
X will,
But in the normal CSV file and all, if you are comparing in the CSV file and all, it will be all the D dimension D1, D2, the features will be there. Okay, and this will be the data point. But here in the representation, we are writing X1, X2, X3 like this. Okay, and this will be the dimension. Okay.
So D cross N.
Did you get the point?
So here D cross M, X transpose will be D cross N cross D. N cross D.
Here the X will be, I'm writing it again. Here your N will be D cross N and X transpose will be N cross D. Okay, right? That is how you are getting see the covariance matrix as D cross D. So this I was telling from the starting. Why? Because it's a XX transpose, right? So that's why you are getting D cross D, and this all started from here only because the D, the multiplication we have the time complexity as D cube. That's why we want some other method to calculate the eigenvector. Okay, and that is why we are doing this. I hope this is clear. Okay, let's. So we came up with three equations. I'll just write it all the equations. So the equation first. Can somebody tell me what we got in the equation one? Wk equals to x into alpha k. What was the equation second? Equation second, can somebody tell me? A times alpha k equals to
lambda
times
alpha.
Lambda times k. Okay, I thought we left n, right? N was there, right, from the starting. Because n came from this side, right? I guess we missed that. It should be there somewhere. Yeah, n is there, right? N should come at that side. So n should be there everywhere. Okay. And then the equation third is what? Equation third is it should satisfy alpha k ka transpose A into alpha k. Right? To calculate the alpha k, it should satisfy both the conditions. Okay. Okay. So now we'll come up. So this is the whole three equation that we have got, and we are just doing it to calculate some other method to calculate the eigenvalue vector.
So equation 3 is 1, right? That is 1 is equal to alpha k. Or is it something different?
This one? Okay, this one we got it from here, right?
No. Equation is 1 is equal to alpha k transpose into A. This value is A, or what is that notation?
This matrix A.
Left side. What is that?
This is 1.
L or 1 or what?
1. This is 1 now because we got it from here, right? Wk transpose Wk equals to x alpha k ka transpose into x alpha k, right? And this is 1 because this is a unit vector, so this is 1. And then we have got alpha k transpose x transpose x transpose x is A, and then alpha k, right?
Yes.
This is from where we got. Okay, and now we are coming up with some fact. So this is fine, but some fact is what? You already know if you have this C covariance matrix as. So what is the covariance matrix? Okay, tell me. 1 upon n.
X into X transpose.
X into X transpose, right? Okay, so whatever the eigenvalues, let's for example for this you got eigenvector as W12 WL. So you got some L eigenvector. So you would have got eigenvalues also, right? Eigen L, right? So for NC, and if you have NC equals to X transpose, for this, what will you get? The eigenvector, what you will get? For this matrix, what you will get? X into X transpose. So you got 1 upon X. For this matrix you got, right? For this matrix you got W1 till Wn. So if you are doing any multiplication, any scalar multiplication, I don't think so there will be any change in the eigenvector, right? So the eigenvector will be same, but what will happen to the eigenvalues? So the eigenvalues will get n time, right? Is this clear?
Yes, sir. Yes, sir.
You can try out with some 2 cross 2 matrix, okay? If you are like not able to understand, maybe after this lecture, you can understand with some 2 cross 2 matrix you can see, and then you can just multiply the matrix with 2 and then check whether what's the difference between the eigenvector and eigenvalue. Okay. Now, and for the A matrix, what was our A matrix? X transpose X, right? So for X transpose X, what you'll get? You'll get a different eigenvector, that is for sure. But what will be the eigenvalues? The eigenvalues, the non-negative eigenvalues will be same, right? Non-zero eigenvalues will be same, right? That we have discussed in the starting itself. Maybe you would, in the machine learning foundation also you would have read. Is this clear? Should I proceed further?
So here the scalar value will be lambda 1 up to lambda n? Or
What? This will be n lambda 1 till n lambda n.
So we have assumed X transpose
so
as
again,
C.
n is multiplied here. Here also n is multiplied.
What? Here also n is multiplied, because see, the eigenvector you were getting same, right? Non-negative eigenvector will be same, but what A is also the same, right? C was what? 1 upon n x transpose, right?
Yeah.
So for x transpose, what? So for n here also it will
n
be
times c, n times
right.
c.
It will be same. So yeah. So what else? Somebody was asking something else, right?
No, sir, it's clarified. Yeah.
Okay. Okay. So yeah. So this is fine. And so what's the issue now? So if let's for example this BL, whatever the eigenvector that you are getting from this matrix X transpose A, and whatever the eigenvector we are getting, that is a unit, right? So the one equation that we have got, okay, so let's see whether that is satisfying our this equation or not. So here for this equation, from equation second, how will it satisfy the equation second? The equation second is what? K times alpha K, sorry, this is A. So don't get confused, this is A times alpha K equals to n times lambda K, right? Alpha K, correct? Sorry for that. Then if it's satisfied, if let's for example this, the eigenvector that you're getting for this A, let's that satisfy that.
Sir, I have one more doubt, sir. In this A into alpha K is equal to n lambda K alpha K. Can we cancel alpha K both?
No, see, if you have, like for example, if when you calculate the eigenvector, so do you cancel that? So A is a multiplication and then it is getting multiplied with some vector, okay? And this is some constant getting multiplied with some vector, okay? You can't cancel that, right? Let's see in the eigen equation what you generally write. This is a matrix. C is a matrix multiply with eigenvector equals to some scalar quantity and then again vector. Do you cancel this? You
No,
don't
sir.
cancel
Thank
that,
you.
right?
Thank you for clarity.
Okay. Okay. So, and if we have to, if this equation is second, so to satisfy this equation, let's try to get the value of alpha K in term of beta k such that it satisfies this equation. Okay, did you get the point? I need to get the value of alpha k in term of beta k such that it should satisfy the value of beta k. So let's, for example, from the lecture itself I'm taking, I have, so there the alpha k was what? Beta k upon root times n lambda k. If you'll just put the values, whether see whether this is satisfying or not. Whether are we missing something or what?
Nothing, sir. We require to make this right hand side also root of n lambda k.
So this is what I am telling. If we need to take out the value, okay. So we have other equation also, right? Equation 3. That is 1 should be equals to. What was the other equation? Alpha. Alpha k square alpha k, right? So this is satisfy both. Okay. And if we'll take out the value of beta k from here to satisfy the equation first, the alpha k value would be.
Sir, is it square or transpose?
Transpose, sir. Transpose.
Okay, sorry.
Alpha k transpose.
Okay, yeah, it's a transpose. Okay, so if you will set the value of alpha k equals to beta k upon root n lambda k, then it will satisfy the equation. Okay, so at least we have got the value of alpha k from beta k, and beta k was what? Beta k was what? Beta k we have got the eigenvalues from where? From calculating the eigenvector of what? X transpose x, right? Is it clear to everyone? And X transpose x is what? N cross n, and this is much, the time complexity of n cross n is what? Can you tell me the, if for d cross d, the time complexity of dq, right? For this, what will be the time complexity?
It's
ONQ.
Right, so this will be nq. And here if you have the number of dimension far less than, so number of data point far less than the number of dimension, then this is much better than calculating bk, is much better than calculating sorry, not bk, so calculating the eigenvector of this matrix is much better than calculating the eigenvector of that d cross d matrix, right? Because this will take much less time, right? So whenever we have a very higher dimension, this method can be used to reduce the time complexity. Okay, is this clear to everyone till now? And this, the conclusion somebody told in the starting itself. So this is what we came till here, and it took almost 1 hour to go through that.
Sir, but if we are having features less than a number of samples, so we can just use the earlier.
On this is not going to help you. Yeah, in those cases we make your work tedious, right? If you have already the dimension lesser, then why are you going to do that? Yeah, go ahead.
So the lambda k is equal to beta k by root of n lambda k. So
Yeah.
here, do you need to remember, or is it a evaluated, like calculated one, like derived?
No, you don't have to remember that. See, here we are doing manually. You just have to understand that. But whenever you will use the just a simple library of PCA, and you can do the hyper tuning. Okay, so you can do everything there. Okay, so you don't have to remember, but yeah, here we are just reading it manually, and you should be aware of that. How can we reduce the time complexity? Okay, so while to reduce the, whenever you will see, okay, if you have the data set and that data set consists of in the form of like images, mostly the images form of data set is because those got converted into pixel, you'll be converting it into the pixel value. So there the dimension will be very huge, like 1 million, maybe 1 million, those type of, so in those cases it will help you. Okay, So I'll just write all the steps here at one. Okay, so this you can refer to the lecture itself, or should I write it like?
Yes, sir, please write it. So at one place we'll be able to use it.
Okay. So what you can do is you can calculate the A matrix that I told you. Step 1 is what? You can calculate the A matrix, and that is X transpose X. Okay, that will be in the n cross n dimension. Okay.
Sir, is there a
Step
specific name for?
what?
Is there a specific name for this A matrix?
There is no specific name. I don't know. Maybe normally that is uh, known as that is represented in the form of Kij, but there is not specific name for this. The kernel matrix, the kernel PCA, that will be reading later, but for this matrix there is no specific name.
Okay, sir. Okay.
Okay, then step 2 would be to compute the what? Eigenvalues and eigenvectors. Right? And the eigenvector will come in the form of what? Beta 1 to beta n. Right? And the eigenvector will be in the form of this. Eigenvector will be in the form of eigenvalues will be in the form of n to n lambda n. And then you need to do the calculate the value of alpha. What is the value of alpha? That is step 3. Alpha k is what? Beta k upon root of n times n lambda k. And then you can calculate wk, where alpha, right? So this is what step is. Okay, so somehow we have managed to reduce the time complexity, right? So we have reduced time complexity from dq to nq, where d is very 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 large, okay, as compared to n. Okay, is it clear? Okay, I guess somebody has asked some doubt or what. Okay, yeah, Dipender Pratap Singh, do you want to ask something?
Yes, sir. Where relation of step 3 comes, it's like alpha is equal to beta k upon under root lambda.
What?
So,
Yeah, in the fourth step, the third step will be used. Yeah.
sir, how the third step will come?
What? Because
How
to calculate the WK, we need alpha k, right?
No, sir. How can we say that alpha k is equal to that relationship beta k upon under root of lambda?
I told you there, right? With the help of, there were two equations that should satisfy this alpha k, and from there we came to know about the beta k. There were two equations, right? You can just check it once more. No, there. Okay. So there was some equation from here itself. Okay. We came to the conclusion that if we are putting alpha k equals to beta k upon root n lambda k, it will satisfy both the cases. So here only we came to know that. Okay.
Okay, so we are guessing that it should be.
No, it's not guessing. In the lecture itself, sir has calculated that. Okay. So it's not guessing. This is the exact value. We are not guessing the value.
Okay, sir.
I just wrote it directly. Yeah, I just wrote it directly.
Okay.
Yeah. So till now, I guess this is clear, right, to everyone? Yeah, Wajid, somebody you asked. Yeah.
Yes, sir. Yes, sir. What is the relation with the lambda 1 and lambda 1? Can we, lambda 1 is an eigenvalue of that x transpose x. So that means we have to multiply each eigenvalue multiply by n, or is it?
Lambda 1 is the eigenvalue.
Lambda 1 is the eigenvalue of x transpose x.
Okay,
Then you take
lambda
below
1
eigenvalues.
Transpose x. No. For x transpose x, n lambda 1 is the eigenvalue.
So what is lambda 1 then? That's my question.
Lambda 1 is the eigenvalue corresponding to, if you are considering the covariance matrix.
Covariance matrix. Okay. So lambda 1 is an eigenvalue of covariance matrix. and we have to multiply that eigenvalue by n. That will become eigenvalue of x transpose x.
Even n lambda 1 is the, or if you are writing n c na, n
Yes,
times
yes,
covariance matrix, there also the n lambda 1 will come. The
yes,
eigenvalue
yes.
will be n lambda 1 times only. Okay,
So
so this is a basic method. Whenever you read
yes,
linear algebra, so if
yes,
you have
sir.
x transpose or x transpose x, so whatever the value, like for example, let's for example you have, this is in the 4 cross 4 and this is 3 cross 3. So eigenvalues, if we are getting, let's for example 2 3 4 0, so here the eigenvalues will be what, 2 3 4. Okay, so this is what.
Yes.
Okay, so all the non-negative uh, or non-zero value will be the all the non-zero eigenvalues will be same for this x transpose x and x transpose.
That
Okay,
will be okay.
yeah. So I guess this is done, right? Let's move to the next part. Or do you have any doubt? You can just ask me.
So
So
just
the
scroll
first
up,
issue we have
scroll up a
fixed
bit,
that.
sir. Can you scroll up a bit, sir? A little bit for a couple of seconds. I just
Okay.
make a note of it. Just where you have written the. Yeah, just 1 second.
Okay. So I guess this is fine, right? Can we move further?
Sir, excuse me.
Yeah.
So what I had actually asked in the chat also, sir,
Okay.
if x transpose x and x transpose have the same eigenvalue, but you stated
Mhm.
they may have a different eigenvector, right?
Yeah, yeah.
Then now our covariance matrix, like the vector corresponding to the largest eigenvalue, is giving the direction for the her maximum variance, right? Like the
Correct.
direction which we require. Now, if
Yeah.
if the eigenvector changes, wouldn't the direction also change?
See, so this is
Huh.
what happening here, right? So beta 1 and alpha 1 is not same, right?
Sorry.
See. Okay, so I have this, right? So we have covariance matrix as x transpose, right?
Hmm.
Okay, so I'm for this I'm getting some eigenvector, right?
Okay.
Eigenvalues I'm getting some lambda 1 till lambda n.
Okay.
And here also I'm getting some v1 to vn.
Hmm.
Correct?
Yes.
And for the alpha transpose x 1 upon n, here the eigenvalues will be same. Lambda
Okay.
1 till whatever the value we are getting. This for lambda
Huh.
d or something. Here it will be lambda n. It depends on d is more or n is more. That will,
Huh.
but the vector will be different.
Huh.
So what's your doubt here?
Nice, sir. Like, okay, V1 might be like if say lambda 1 is the largest value.
Okay, lambda 1 is the largest here also. Okay.
Then V1 would be the eigenvector, the direction of the direction which we need, right?
Yeah, the
V1 would
direction
state
which
the
we need.
direction
Yeah,
which we need.
this is the vector that we need. If we are converting from some d dimension to one dimension, this is the eigenvector that should be
That we need.
our
Now, in this case of lambda 1, like in the second case, it wouldn't be V1. It will be some other U1, right? Like for say
Yeah, it
some
will
other
be u1
vector.
something. It can, yeah, it will be some u1 vector. So where we have told
Now,
it's similar, same. This is not same.
sir,
That
it
can
is
be.
not same. Now, U1 is then if it is not same, then U1 need not necessarily point in the same direction as V1, right? Like we want that
No,
particular V1, right?
yeah, so the direction will be same. Only it will be some scalar multiplication of something.
Oh, okay. It
Yeah,
will not like the values will not be same, but the direction will be same.
yeah, correct.
Oh, okay. This was my doubt, sir. Okay. Thank you. Thank you, sir. You can continue.
Yeah,
I got
okay.
it.
Yeah, thanks a lot. Okay, so shall we move further? Or shall we move to the second issue that is there in this PCA?
Yes, sir.
Okay, so give me 2 minutes. I'll just have a sip of water and then we can start. Excuse me. Okay, so let's start. So we have, so we are almost 7:40. So I'll just discuss the second issue, and then the more explanation and all we'll be discussing in the next meet. Okay. So okay. So you have any doubt in activity questions that you can ask me till now. If you anybody has went through the activity and practice, you can just ask me. I'll just go through some doubts and then we can start the issue.
Sir,
Yeah.
sir, I have question that in covariance matrix we were getting eigenvector as W1 to Wn.
Correct.
In XX transpose we are getting beta 1 to beta L.
Huh. L. Okay. So.
Okay.
So.
Yes.
Yeah. Go ahead.
Is the number of
yeah, the number will be different for both the cases.
equal or different, sir?
No, it will be different because for X transpose X, we have how many D cross D matrix, right? Sorry, N cross N matrix. So for this is N cross N matrix, right? For X transpose we have D cross D matrix, correct?
Yes, sir.
Right. So for if let's for example if so what I told you for X transpose X and XX transpose, the non-zero eigenvalues will be same, but others can have the zero can be there, right? Whenever if for example D is greater than N, then if D is, I told you, right, D if D is like 3 cross 3 and this is 2 cross 2. Let's for example I have the eigenvalues as 2 3 0. So for this case 2 3 will be the eigenvector, right? But here the eigenvalues 0 is there, right? Did you get the point?
Yes. Thank you.
Yeah. So I'll just go through the issue second. So we don't have much time. So whatever I can discuss it like 15 because I need to go somewhere by 8:30. Okay. So that's why I won't exceed the lectures today. And this is weekend, so I also so you can also go like wherever you want to go. So we'll meet on the Sunday. But okay. So I'll just discuss 15 minutes about the second issue. So the issue second is what? Can somebody tell me if we have went through the lecture? What is the second issue?
Dealing with features which are not linearly connected with each other.
Correct. So PCA generally, what PCA does is it generally comes up with the linear combination of the features, right? But if you don't have the linear combination of the features, right, this is F1 and this is F2. Let's, for example, this F1, the data point is related in such a way that this is in this form, in this y is equal to 4x form, such that this is a form of parabolic distribution of the data set. Okay, so here the features are not directly features are not linearly dependent. Like for example, the date your data point is on this circle. So this is a circle with 0, comma 0 as the center and some radius r. So your features will be what? Your features is related at f1 square plus f2 square is equal to sum r square. Right? This is f1 and this is f2. Correct? So here, if you want to have a, like for example, if this is the feature 1 and feature 2, if you want to project your data set on the PCA, on the principal component, okay, so which principal component will you consider? I'm giving one example. This is a vector 1 and this is a vector 2. So which principal component do you think will transfer from like 2 dimension to you need to have only one principal component, and you should not be losing the information more than 5%. Okay, so which principal component you'll be considering if you have the data set like this that is not connected to each other? So like it's connected but it's not linearly connected. So which vector do you think will work out of v1 and v2?
Both, I guess.
Both can work.
No, I need only one out of the two. How does that both? So what is the PCM? I told in the starting I need a direction where the variance would be maximum. Okay, so in which direction the variance is maximum? If you are taking V1, the variance is what from here to here. Even if you are taking V2, so there can be a slightly difference because it's not a complete circle, but like mostly it will be almost similar, right? The variance would be almost similar on V1, V2. But if I need to convert from 2 dimensional to 1 dimensional, and I need not be losing the information more than 5%. So more than 5, I'm telling not more than 5%. Maybe in the first lecture we would have went through that. Whenever you are changing, you are converting, you are reducing the dimension, you should not be like, it's not standard, but in the lectures are told like you should not be losing more than 5% of the information. So you should be, while reducing the dimension, the information you should be acquiring should be more than 95%, right? But here, if you are reducing to some B1 or B2, you'll be able to, most probably you'll be lose the information. For that, you should be needing B1, B2 both. Okay. So wherever you will get this type of a data set, so you worked on simple data set, like the data set was like this, or maybe the data set was pretty like this. Okay. So you were able to get a line or best fit line where where you were able to know the variance is maximum or the reconstruction error is minimum, right? But if you have a data set which are like not linearly connected, so those are like in the form of some, this features were like polynomially, like how this, if you will see this feature where most of the, it resembles a circle, the data set resembles a circle. In those cases, you'll not be able to use the linear PCA, okay, to get the principal component. For that, you should be needing some kernel PCA, like some PCA, some sort of other method, such that it should transfer your F1 and F2 onto some bigger dimension, and then from there on the bigger dimension, that should be a linear subspace. Like it should be some in the form of some linear, so that the PCA can work there. So from F1 to F2, you can just transfer that dimension to some bigger dimension, like 6 dimension or maybe bigger dimension. and on that bigger dimension, the PCA will work, and then you can, if you want to visualize that, you can reduce those dimension from bigger dimension to again to the smaller dimension, just to visualize that whether it is the PC is able to classify, or maybe it has worked nicely or not. Did you get the point? What is the issue here? Yeah.
Shall I repeat, sir? That
Yeah, you can repeat
that example. What lecturer has shown in that circle, which it is there, we are unable to choose whether V1 or V2.
Correct.
That it is transformed into 6-dimension vector, such that we can make that particular represented in a six direction vector R6.
Correct.
So when we are seeing some, we are not getting any solution for this type of non-linear points. Then we require to transform it into higher dimension, right?
Correct. Because so this was the first assumption generally we make while using PCA, that your data set should be linearly separable. Okay. So this was the first assumption that we generally, but here whenever the data is not linear, so in those cases you will find difficulty in this dimensional reduction technique. So for that we have other technique like the kernel PCA. Okay, the kernel PCA can be of 2-3 types, but here basically you'll read about the polynomial and the KBF. Okay, the
So can
Gaussian one
you
and
just
so
can you just tell me that how can we visualize that data points are non-linear without plotting it?
yeah, without plotting it, you'll not be able to know whether the data are having manually. You can't say. That is the first thing. You
So
should be
if
using.
just data set is given, we can't just say that we can use
you
the
can't
kernel
say.
method.
Nobody can say that whether this. Yeah, nobody can say that. So with the help of like different libraries, different hyper tuning, whatever you'll make, till that time you'll not be able to know whether how does that your data set behaves. Okay.
Okay.
And there's
So
no like
without that information, we cannot apply that
no,
kernel method.
without
That
otherwise, if we are able to know that how these are related, we would have got some mapping like phi that we are searching for, that phi that you would have went through the lectures.
Yeah.
We are needing that phi mapping stuff, that function, right?
Yes.
Okay, we are not able to get that. So for that itself, we are going for some different method, and we are we are searching for some polynomial kernel or some Gaussian kernel to just get those ideas, to get the dot product of those the transform data point, right? So that's why with the getting the data, you can't be able to say much about like how can you transform in which dimensions. So those and all things you can't say with the help of only uh, the data set that you have. Okay, that's the one thing. Yeah. Any other issue anyone have? Okay, so yeah, so this was the issue uh, in the PCA. So I told you in the PCA we have the one issue was the time complexity. And the other issue is what? Non-linear. When the data are non-linear. So for this, we already fixed that. So we fix that. How are we fixing that? We are fixing that with the help of X transpose X matrix. Correct? We are reducing from D cross D dimension to N cross N dimension. Right? Here also we'll see how we'll fix this. So this will fix this. This also will fix. Okay, with the help of kernel PC and all. Okay. So I'll stop it here, and then we'll discuss how will we fix the whenever the datas are non-linear in the Sunday class. Sunday we'll meet at 10 to 12. Okay, so in today's session, if you have any doubt, you can just ask me again. So I'll just give you 10-15 minutes. If you have any doubt, you can just ask me. Is this fine to everyone? And I'm not feeling like that. Yeah. So yeah, you can ask your doubt. Anybody is anyone is having any doubt? If you need this slide also, I'll just upload it maybe on the Google Drive and then share it on the discourse. But it's all there in your lecture itself. Anyone having any doubt, you can just ask me. Yeah.
Yeah, sir, I have one doubt on this non-linear path.
Yeah.
For the non-linear, there is a transformation required for the data since it is a non-linear following.
Yeah, correct.
So, what type of transformation that we have to decide? Like, so now you have drawn a circle. I mean, the data points are plotted in a circle fashion. So, how do you decide the mechanism of the transformation function?
Yeah. So so function you can't you can't get the mapping that exact function. How are you going to map that from like f1 f2 dimension to some bigger dimension, 6 dimension or 7 dimension, right?
Yeah.
Okay, but we have something like we need some we have like I'll let you know in the next session, but we have like kernel function, one function that will give us a matrix, okay, and that will resembles the mapping, whatever the product, whatever the stuff that you would have got from the mapping, okay, that you will get from the kernel function. So we have like two types, mostly we use two types of kernel function. If you want to explore, it's like basic library kernel pca itself with some hyperparameter tuning you have to do, okay, that you can explore that in the Colab if you work on that. But basically we use this like two types of kernel that you'll use in svd also, like support vector machine, that when we'll go to that in fifth or sixth week, okay. But there is no hard and fast rule how will, from some two features, how are we going to get project the data set onto some higher dimensions, okay.
Okay.
It's just that hit and trial stuff.
Okay. Thank
Yeah.
you. Thank you, sir.
Yeah. Okay. So should I close this, or if you have any doubt, you can just ask me. Otherwise, I'll close it. We'll meet in on the next session. Till that time, I'll just write it my Gmail ID. You can just mail me if you have any issue, anything related to my lecture, okay, or anything, any doubt you have, you can just ask me on the Discord also. You can just, I'm just writing my mail ID on the chat box. You can just copy that and can use it if you have any doubt any time, okay.
Yeah, sir. Please share it.
So it's like Vishal @ study.iitm.ac.in. Okay. Yeah. So I just wrote it in the chat box. You can just copy that. So the remaining part we'll discuss the issue second, and the kernel part we'll discuss in the Sunday's class. That can go like more than 2 hours, but that is fine. So today I'm not well also. I don't know how did it happen, but yeah. So, and I need to go somewhere also.
Okay, sir. Take care. Thank you.
Okay, thanks. So today's session, you don't have any doubt, right? So I'll just close it then.
Thank you, sir. Take care.
Okay, thanks everyone, and goodbye.
Thank you.
Thanks, Lakshya. Thank you. Thank you.